Chapter 5, Number 9. A 42-kilogram parachutist is moving straight downward with a speed of 3.85 meters per second. If the parachutist comes to rest with constant acceleration over a distance of 0.75 meters, what force does the ground exert on her? If the parachutist comes to rest over a shorter distance, is the force exerted by the ground greater than, less than, or the same as in Part A? And explain. So, I'm going to do this actually two ways, because where this arises in Walker assumes sort of sets up a wrong way. So we're going to find the net force on the parachutist in Part A and talk about in Part B. And then we're going to go back and revisit the problem with the total force, the actual force the ground would exert. And I'm going to hold out to why that would be the case up until, until we revisit it. So here is the ground, and here is our parachutist who has just reached the ground with, I guess, her parachute, yay. And she's moving, originally she's moving downward with some initial V0. And then eventually, of course, eventually her legs buckle a little bit, and then she's at rest. So I guess we'll draw her a little lower, and the parachute has come over here or whatever, and she's at rest. Alright, and the assumption is that there's sort of this small distance, h, which is this, over which she has come to rest. So drawing it as sort of more abstractly, there was, she is some object hitting the ground, that's her, and then the object, whatever is her, moves to the ground. I'm not sure that really helped that much. But turns out we don't really have to care about what it looks like. We draw a free body diagram, which I'll go up here to do. And the free body diagram, we say, what's going on? Well, there's an acceleration, and if she was moving downward but has become to rest, then she has gotten slower moving downward, so there is an acceleration which is upward, and then that's being produced by a force pushing on her. For the moment, I'm just going to call it F, and the way the problem's set up, they act as if that's the only force acting on her, and so we'd be able to say that the net force is MAY. So F is that net force, is MAY. Now, I don't actually have enough here, because I don't have the acceleration, but I can find it. I can go back to my kinematic equations, and I can do things like, well, I don't have a time, and I don't care about a time. I do have distances, accelerations, and velocities that I know about or care about, so I'll go back to the Vy squared is V0y squared plus 2 times the acceleration times the change in y. We have to be careful. This looks like our projectile equations. Of course, it really is the projectile equations, but A is not G. The projectile equation is this with a particular known acceleration. We don't know the acceleration. We are looking for the acceleration. All right. Actually, we're not even looking for that, but we're not given it. We need it for over here. All right. So then we solve for it, and we say she ends at rest. She starts at some initial speed. Actually, I'm going to solve it symbolically first. So V0y squared plus twice her acceleration. She ends on the ground, and she was a distance h above it. And if we solve this over, we would find that we have 2ay times h is v0 squared y. This is probably starting to look familiar from the kinematic stuff. Whenever you sort of end at rest, you get formulas that look something like this. And we find that ay is v0y squared over 2h. And therefore the force, going back up to here, the force is just the mass times that, mv0y squared over 2h. And so we can put in some numbers. She's 42.0 kilograms. The speed is 3.85 meters per second quantity squared. And the height is 0.750 meters. If we look at our units, we have kilograms times meters squared over second squared over meters. So we get kilograms meters per second squared, which will work out nicely. That is what we want. And numerically, we get 0.75, 415 newtons to the right number of sig figs. And the newtons comes from just combining the kilogram meters per second squared. This does not agree with the back of the book. If you looked up the answer there, you got a different number, and that's okay. We're going to explain why. Like I said, this problem ends up early in the chapter, before really Walker has covered some of what you need to do this, and we'll talk about that in a second. But we can still answer part B, and we can say, if the parachutist comes to rest over a shorter distance, then h would be smaller. So this would be a smaller number, but I'm 1 over that, which would mean this would have to be a larger number. As h goes down, h decreasing implies f increases. The shorter the distance you stop over, the harder it is to stop, the more the ground has to push on you. So that's fine. So why don't we get what the back of the book has? Because what we've done is correct, except for one interpretation. Our free body diagram was incorrect. Our free body diagram, which is the parachutist, there is definitely the ground pushing upward, which I'll still call F, but at the same time there is the earth who is pulling downward on the person, which I'm going to call S sub G. This is the thing called the weight, which hasn't been covered in the textbook as of this moment in this chapter, but we cover in class, and so we'll be able to handle it. And so when I write the formula for the net force in the y direction, I have to go back to the diagram and I have to say, oh, well, that has F pointing upward, but then we have FG, and it's pointing downward, so we get a minus sign between them. We do the vector addition of these things, which means direction matters, so we have to subtract off the magnitude of the weight. On the other hand, it is still true from Newton's second law, it's still certainly true that the sum of the forces has to equal MAY. So our answer from before is actually still true. Our answer before, 415 newtons, which we got from the previous page, that was still MA. That is correct. It's our interpretation that that was the whole force that was incorrect. Instead, I go over here and I can start saying, well, then the force that the total or net force is 415, and the thing I'm looking for, I don't know, but I can find the weight of the person, and because the weight of any object, F sub G, is always just the mass of that object times G. So this is going to be times her 42 kilograms times the 42 kilograms times the acceleration in free fall, because the weight of any object is your mass times the acceleration of free fall. And so with a little bit less color magic here, we'll have 415 newtons is F minus 412 newtons, and therefore the thing we wanted, F, is 415 plus 412, or 827 newtons, which is what Walker lists in the back of the book. So this is clearly what was intended, although, like I said, where this problem falls in the chapter makes that a little strange. He hasn't introduced free body diagrams, he hasn't introduced the normal force, he hasn't introduced the weight. So it's kind of strange. Also, pedagogically, picking an acceleration that gives you that the force is almost exactly the same as her weight, it has no deep meaning here. There's no particular relation between them. There's no reason. He just ends up with, he just picked numbers where it happened to work out that way and apparently changed them. Our answer for part B remains the same, because if we decrease the distance, then we will, as we said before, we would increase this, and therefore we would increase this. So we still have that h going down, right? A lower h implies a greater f, just like before, and this weirdness about the weight doesn't actually matter.